Now we'll be starting on looking at the form of the oceans, leading into why they are the form that they are. So get to the Chapter 2 PowerPoint here. Planet Oceanus. Aren't we on Earth? Well, we live on the land, and so we do tend to think of our planet as Earth, but oceanographers might argue that if you look at the map, actually more of the surface is covered with water than land, and so Oceanus makes an appropriate name. At any rate, taking a look at the map here, from voyages such as Captain Cook's, there was a French voyage not too long after that, getting into Pacific as well. A variety of expeditions. A lot of what's visible on this map would have been known by around 1800. But there are some things not on here. Obviously, Antarctica is missing. No one had gotten quite that far south yet. North Pole region, in fact, some of the areas shown on this map had not yet been explored, and poles themselves weren't reached until after 1900. But overall, land, roughly where the mountains are, things like that, was generally known by around 1800. But the ocean on here is just blue. What's underneath it? Why is there a hole there for the water to be in? That takes knowing something about what the bottom of the ocean is like. And in turn, that requires suitable technology to be able to measure it and sample it. Now, of course, in shallow water areas, people had measured depth there. After all, you don't want your ship to run into a rock. So there was some degree of mapping, but it gets much more challenging as you get deeper. Yeah, you can have a rope, stick a weight on the bottom, toss it over the side, see how far the rope goes. But is that rope going straight down in the water? Maybe not. There were some rather extreme claims of depth made where evidently the rope was going a lot more sideways than down. But even if you do set things up to have a more precise measurement, as the Challenger expedition had, okay, I dropped things over the side of the boat here, and okay, that took 2.5 kilometers of rope. So the bottom there is about 2.5 kilometers down. What about on the other side of the boat? Well, I didn't drop the rope there. It's probably not too different from 2.5 kilometers, but who knows? There could be a mountain or a hole over there that missed with measurement. So it wasn't until having ships specifically going back and forth extensively measuring the ocean floor that we could get a decent idea. And even that, somewhat patchy. Newer technology such as radar and eventually satellites using radar type measurements have given us a much more thorough picture of the seafloor, although there's a lot still to be done. So getting a map like this that shows elevations of the seafloor only about 50 years ago, it was into the 70s before a thorough seafloor map was made, and there's still significant discoveries. Just a couple years ago, a satellite discovered on the order of 1,000 undersea mountains that we didn't know about because measurements hadn't been made as precisely there. And there's yet more work going on even to this day to get a better map of the seafloor. In this picture, the more reddish areas are shallower, and the deeper blue to purple end is the deepest parts. So you can see there's a lot of variation. Seafloor is not just flat and featureless. We have a number of mountain ranges and low, deep valleys and things like that here and there. So based on these variations in elevation and also the forms, is this a mountain chain, an isolated individual peak, what's going on, things of that sort, we can recognize three major types of regions under the ocean. We have the continental margin areas, deep ocean basins, and the mid-ocean ridges. So we'll start close to land, the more familiar bit, continental margin areas. As the name suggests, this includes area that it's basically just like what we've got up on land, just wetter under the ocean, but the rocks material underneath are pretty similar to what we see on land. Also, land sticks up, and what sticks up tends to get eroded and washed down. So we have lots and lots of sediment, sand and mud, that are formed by weathering and erosion of the rocks up on land, washing down, piling up on the edges of the continents. Plus you've got the skeletons of ocean creatures, things like that, which also help build up these layers of sediment. As mentioned before, note the difference in scale. The vertical scale here is 2 kilometers and the horizontal is 200 kilometers. So in reality, this is stretched out much more than what the picture suggests. It's not nearly as steep as what you see there, but if it were stretched out, you can really see it. So keeping that in mind and understanding the diagram. 3 main parts to our continental margins. We have the shallow continental shelf areas, then the drop-off of the continental slope, and at its base we have the continental rise. Continental shelf area is relatively shallow. In fact, if you've been to the beach and waded in the water, you've been standing on continental shelf. At its deepest, generally no more than 200 meters. A meter, again, is a little more than a yard. So 100 meters is basically football field length. It's pretty flat. That'll come as no surprise if you've ever headed to the beach here in southeastern US. You go across quite a lot of pretty flat land before you get to the water, and under the water is not all that different. Some no more than about 20 meters of ups and downs of hills and valleys, things like that. It is getting deeper as you head out into the ocean, but very slowly. If you could stand there and look around, it wouldn't obviously be sloping any particular direction. It would look pretty flat. So underneath the continental shelf, the rock is generally pretty similar to what we have up here on land. How far does it stick out? That varies quite dramatically depending on what part of the ocean you are looking at. In some places it is quite narrow, only about 2 kilometers, a mile and a half or so off the shore. Other cases it may extend as much as 1,000 kilometers. Here in the southeastern US, it's pretty wide. Just where the edge is, sea level does vary up and down. Go back before the ice ages, and there was more water in the ocean, less than ice, and sea level was higher. At peak glacial periods, lots of water locked up in the ice, sea level was a lot lower. Practically all the continental shelf was land. So there are ups and downs, and just how deep it is, how far out it goes, or how much of what's currently coastal land becomes underwater. That varies quite a bit through geologic time. Land, we've got the rocks eroding, we've got things like dead leaves and stuff like that washing down. So typically that's carrying a lot of nutrients down into the ocean. Compared to out the middle of the ocean, over the continental shelf typically is relatively rich in nutrients, and most fisheries are above the continental shelf. The shelf has a thick layer of sediment. This includes bits and pieces of rock eroded from the land, and of course remains of ocean creatures piling up as well. On this map, what would you think would be the continental shelf? Well, not too hard to figure out. Continent's in black. So the continental shelf colors would tend to be in the kind of pinkish stuff. Moving down from there, we get to the continental slope. Top of the slope, of course, is the outer edge of the continental shelf, so it will be, again, around 100 to 200 meters depth at the top. And it goes down a couple kilometers more, maybe as much as 5 kilometers, depending on where you are in the ocean, all the way down to whatever the deep part of the ocean is. The continental slope, it's deep enough, it's dark down there, but if you somehow could stand there and look around, then you would definitely know you were on a slope, similar to the slope on a hill or mountain as you're driving. The continental slope extends around 150 kilometers, 100 miles roughly, out beyond the end of the continental shelf area. And most of the slope is made up of thick layers of sediment. If it's washed from the land out onto the shelf, makes it all the way across the shelf, then it will go down the slope and eventually be ending up in the deep ocean if it doesn't get stuck and stay somewhere in between. Here and there on the continental slope, there are large, deep submarine canyons that cut into it. These canyons may be anywhere from 1 kilometer to about 15 kilometers wide, cutting all the way down the slope. So these are quite substantial canyons. If we could see them, they'd be very impressive. Many are larger than, say, the Grand Canyon. In these areas, there are steep cliffs and other more extreme slope compared to the general slope of the continental slope. Often these can be found offshore from where major rivers flow into the ocean. The river flow would have contributed to erosion, especially at times of lower sea level. As this drop off going into the deep, any sand or mud washing along that gets into the canyon is going to go on down and end up in the deep ocean. So they tend to represent important routes for sediment descending deeper in the ocean. Also, water, depending on conditions, you might have water flowing down or up, or whichever is happening, the canyon tends to provide something of a channel for that. So you often have distinctive water flow around the canyon areas. Our deepest part of the continental margins of continental rises. These are in deep water, over 1 kilometer, maybe as much as 5 kilometers down, depending on where you are. Like the continental shelf, these are very flat areas. Some of the hills get a little bigger, but still very flat. Again, if you could stand there and have the light to see, it would seem flat. You couldn't tell a distinct slope, though it is very slightly getting deeper as you get out into the ocean. Continental rise is on the order of several hundred kilometers wide. Basically, it is the pile of sediment that is washed all the way across the shelf, down the slope, and into the deep ocean. And it grades then into the deep ocean basin areas. What about the deep ocean? So this is out in much of the middle of the ocean regions. Parts of it are extremely flat, the abyssal plains, but there are a variety of bumps, abyssal hills, seamounts, and also the deep sea trenches. The deepest parts of the ocean are part of this deep ocean region. The abyssal plains are by far the flattest large regions of the Earth's surface, very, very level, more so even than the major plains up that we see on land. Sediment is present, but somewhat thinner than close to land. After all, quite a lot of sediment is stuff eroding off the land. The further away from land you get, the less of that there is. Some does manage to wash all the way across the shelf, down the slope, across the rise, out into the abyssal plains. But a lot of it either comes from the fine dust that can be blown all the way around the globe on the wind. You may remember people getting all excited about dust from the Sahara blowing into the US earlier this year. Well, not all of it made it across the ocean. Some of it landed on the sea floor. Also, there's biogenic material. From the name, not too hard to guess what that would mean. Once again, are skeletons and other bits from living things that live up in the water. Much more life occurs near the surface of the ocean, but when that dies, the pieces can sink down and contribute to the layer of sediment down on the deep ocean floor. Abyssal plains are characteristically at least 3 kilometers down, up to around 5 kilometers towards the deep end. This is a significant part of the ocean surface. Looking on the map here, deeper areas, so you can probably guess these would be our deep blue to purple areas out in much of the middle of the ocean. Although overall the abyssal plains are very flat, there are some types of bumps there. Arbitrarily, we decide that if they're less than 1 kilometer tall, then they are hills, abyssal hills. And if they're more than 1 kilometer tall, then they count as mountains. Up here on land, well, it depends on where you are. Just south of campus, for example, we have Jolly Mountain and Abe's Mountain that are quite a lot less than 1,000 meters, but, well, that's about as tall as anything around, so we tend to call them mountains here. If you were, however, to say to go out to western Colorado, nobody would pay attention to them because they've got much taller mountains. For the bottom of the ocean, well, there's nobody there to ask what they think is a mountain, so we've just said 1,000 meters is the cutoff. It's just a hill below that counts as a mountain above that. Seamounts are what we call any sort of underwater mountain, at least 1 kilometer tall. Now, of course, if it makes it all the way to the surface, then we call it an island. But if it's underwater, then it's a seamount. Both the abyssal hills and seamounts characteristically are old volcanoes of some sort, or there are active volcanoes down there as well. A special category of seamount are the geodes. These are flat-topped undersea mountains. Why would they have a flat top? That was a puzzle when they were discovered, and we'll see how the solution contributed to understanding how the seafloor works. Deep sea trenches. Interesting places, a number of unusual features. These are the very deepest parts of the ocean. At the top, at the edge of the abyssal plain, they tend to be around 5 kilometers down or so. At the very deepest, they may reach as much as 11 kilometers in depth. The deepest spot known in the Mariana Trench. Measuring precisely that deep is tricky. It at least gets to almost 11 kilometers. There have been some claims of making it to that. They're not all that wide, only as much as 100 kilometers. That's around 60 miles wide at the widest, but they're relatively long structures. They're areas of geologic activity. Major earthquakes are common around the deep sea trenches, and there are volcanoes near them as well. The deepest parts of the ocean aren't the places farthest from land. Near the deep sea trenches, they are characteristically associated either with island chains or with the edge of a continent. Not surprisingly, there's a hole in the bottom of the sea, you tend to get stuff in it. Yes, there's a song about that. And in this case, most of what's in the hole is sediment, sand and mud. So we have quite a lot of sediment that piles up in the bottoms of the trenches. Again, deep sea trenches, these are those deepest parts of the ocean. The submarine canyons, those were those deep valleys cutting into the continental slopes. Those are much shallower. They're still deep as far as if you were to try to swim there, that would be quite difficult. And you definitely wouldn't make it down to the deep sea trench, well, at least not in any shape to be able to report on the experience. But two different things. The canyons cut into the slopes. The trenches are these very, very deep ocean areas. For comparison, Mount Everest is under 9 kilometers tall. So if you could somehow cut Mount Everest off at sea level and drop it into the ocean, there would be over 2 kilometers of water, more than a mile above its top. So the deepest parts of the ocean are noticeably deeper than the tallest parts of the mountains. Our last major part of the seafloor are the mid-ocean ridges. These form a mountain range that connects through the oceans, circling all the way around the globe. Roughly a third of the ocean floor can be considered part of the mid-ocean ridges, and then again it's around a third for the deep ocean areas and a third that would be continental margins. If you track all the way along the ridge, following all the zigs and zags, you can consider it to be the longest mountain chain on Earth, going over 60,000 kilometers. The middle part, the ridge crest, the highest part of the ridge, and then you have the flanks sloping down, gradually grading out into the deep ocean basins beyond. Despite the name, mid-ocean ridges are not always right in the middle of the ocean, though they sometimes are. Looking at the picture here, well, process elimination, we've covered the other colors, so you can figure out that those would be the mostly yellow to green into light blue mountain chains that are sneaking around the globe here. You can see in the Atlantic, it is pretty much in the middle of the ocean, and that's where it was first discovered. After all, you've got quite a lot of folks going back and forth across the Atlantic between North America and Europe. Pacific and Indian Ocean understandably a little bit slower to get thoroughly sampled to map the ridges there. Out on the flanks, ranging from about 3 to 5 kilometers down. As you get further from the middle, there's more sediment. Why? That's something that we'll be looking at pretty soon here. Lowest sediment is towards the very center. The flanks gradually grade into steeper ridge crest along the middle and into the abyssal plain as you get out to either side. The crest, shallower, deepest maybe as much as 4 kilometers. Generally shallower, 2 to 3 is more typical. A few places it actually reaches the surface, most noticeably in Iceland. Along the ridge crest, there's very little sediment. In some places you see bare volcanic rocks. Like the trenches, the ridge crest is geologically quite active. You have a lot of volcanism and earthquakes, although typically not nearly as dramatic for either one as you get associated with the trenches. You have cracks with hot water, hot springs on the bottom of the ocean. A number of distinctive features along these ridge crests. The very center is not the tallest point. Instead, there's actually a valley running down the middle of the mid-ocean ridges. Sides are relatively steep, and this shape is characteristic of a place where we have two sides moving apart, and the middle then drops down in between. We can see these on land. Today, probably most famous would be the African Rift Valley system. The Great Lakes in East Africa are in valleys of this sort. The Dead Sea, another example, at extreme salt lake along the edge between Israel and Jordan. Lake Baikal, or closer to here, you can see one easily if you go to Chapel Hill and head towards Durham. Towards the east side of Chapel Hill, it actually is a hill, and as you drop down that hill, you are going down the side of an old rift valley. So as the picture illustrates, easy to imagine if the two sides are pulling apart, what's in between will tend to drop down. The mid-ocean ridges have a number of noticeable zigs and zags. These are known as fracture zones. The faults that cut across these are known as transform faults, where one block of the earth is sliding past another. Let's see, that sort of movement. And then as you move out from the ridge, we move from the faults to cracks where things aren't moving, and those cracks are known as fracture zones. These extend out into the flanks of the mid-ocean ridges and eventually disappear into the abyssal plains. Looking from above, if the red bits here are the mid-ocean ridge areas with the rift valleys, we have rock moving out sideways. Look a lot more at that soon, but for now it does move. And so with these zigs and zags, we've got patches where rock's moving one way on one side, the other way on the other, and this creates our faults. And then the fracture zones are extensions of the cracks from the faults on beyond in either direction. These may range anywhere from about 10 to 1,000 kilometers out on either side. And these cracked areas aren't quite the knife edge the picture suggests, there's zones perhaps a few tens of kilometers in width of cracked and broken rock. So, ocean floor. It's not just like the land, only wet. There are distinct features there. Why? Ironically, a lot of this distinctiveness was first noticed by Marie Tharp. She was working in a lab studying marine geology. Due to superstitions, she wasn't allowed to go out on the ships and be a part of the data collection. Instead, she was stuck back in the lab doing the mapping, compiling all this data. Not getting on the ship, that probably wasn't as fun, but that meant that she was the first one to see the big picture as she put these data together into forming what became the first deep ocean thorough map. And as she looked at the pattern, she realized large-scale structures and thinking about what these could mean geologically, and was one of the early ones recognizing some of the patterns involved in plate tectonics. But at any rate, why do we have difference between what's up on land and what's under the oceans? Since this is part of the physical Earth, we need to look a little bit into geology here, knowing something of the structure and history of the Earth. Earth is made of a series of layers, often referred to as spheres, since they're close to circular in different directions. And these different layers have different chemistry and physical properties as well. How would we get these layers formed? Earth, initial creation, we have lots of big rocks from space colliding, building up. And also there was relatively high radioactivity. And the combination of heat from those would have been enough to melt the Earth, especially had a roughly Mars-sized piece crash in, and that would totally melt the Earth from that collision. With things being melted, heavier stuff could sink, lighter float, and this led to our series of layers. We have a thin outer crust, and then of course we've got the water and gas layers above that are the main focus of our class here. But the rocky bits underneath, we have a thin crust layer, a thick rock layer, the mantle, and then thick metal-rich, mostly iron layers, the outer core, which is actually melted iron sloshing around down there, and a central solid iron ball, the inner core. What they're made of and the state. I alluded to just now both of those. These give different properties to our different layers. So zooming in more closely, our atmosphere, relatively thin compared to the solid part of the Earth, especially if we're talking about atmosphere that's more than a tiny bit of gas. Yeah, it's more gas than outer space, but still not much. Likewise, the oceans, at most, again, 11 kilometers, so relatively thin there. The crust layer is also pretty thin. Continental crust, as you may be able to read here, 35 to 50. Ocean crust, 3 to 10 kilometers. But continental crust is thicker. That's an important difference that we'll be looking at here. Mantle, again, made of rock, basically solid rock. Yeah, there's a little bit melted here and there, but not that much. And then the liquid melted outer core, solid inner core again. Okay, I've been telling you all about what's way down deep inside the Earth. How do I know this? I have not been there. Nobody's been there. So how could we know that? The deepest holes drilled have not made it beyond the crust. This was actually a bit of a competition back in Cold War days. See who could drill through the crust the first. Somehow the race to get up to the moon got more attention and was actually finished. Okay, US made it to the moon first, so Soviet Union decided they'd keep on drilling down and see how far they go. They actually got over 12 kilometers down, but eventually stopped. The project actually lasted longer than the Soviet Union. It was going into the early 90s before they finally stopped. There are projects right now that hope to actually drill all the way through the crust, but that would only reach to the very top of the mantle. No way we're going to get much beyond that, certainly never drill down to the core. So what evidence do we have? Well, one of the most important pieces of evidence is studying the patterns of earthquake waves, especially if there's a big earthquake. The waves can travel all around the globe, and looking at details, there are different types of waves involved in earthquakes. What's the timing like? Where are they faster or slower? By making lots of measurements, you can detect that waves are going a little slower here, a little faster there. Work out a picture of what's underground. A little analogous to using ultrasound and looking at stuff inside a human body. Meteorites give a clue. They would have formed in the same general part of the solar system as the Earth, and so give a picture of what's there. In particular, meteorites tend to have a lot more iron in them than your average Earth's surface rock. Iron's not rare, but it's not as extremely abundant as is typical meteorites. That suggests that there should be a lot more iron somewhere in the Earth, and if it's not at the surface, then it would have to be deeper down. Similarly, by measuring how Earth interacts gravitationally with the sun and moon, things like that, we can calculate how dense the Earth is. And the average density for the Earth is a lot higher than the density of the rocks we find here at the surface. This tells us that, once again, down underneath, there's something denser, different from the surface. We can do experiments, putting samples under extreme temperatures and pressure, and seeing how these behave, getting a picture of what things might be like down there, and say compare those results with the patterns from the earthquake waves, measuring Earth's magnetism, gravity, things like that that relate to stuff down inside the Earth. We can also do computer models and see what the computer suggests. If the Earth's interior is like this, what should we see? Do we see that? And so by putting these types of evidence together, we've got a decent large-scale picture of what's inside the Earth, but a lot of detail. There's still much to be found out more specifically about how things work deep inside the Earth. Okay, going down in the Earth, it's characteristically getting hotter as you go down. This can be observed at a small scale by mines. The deepest mines, I think current record holders, some gold mines in South Africa, and they have to have extreme high power air conditioning. Even with that, any one miner can only work for a couple hours before it has to have a break due to the heat there. We also have increase in pressure. The further down you are, there's more rock on top of you, and all that pushing down, that's more pressure. How about increasing temperature? what's that tend to do? If we start with a solid, well, as Olaf here knows, it'll melt. No, I'm not sure Olaf actually figured that out, but we do. Increasing pressure, on the other hand, tends to make it harder for things to melt. Atoms, molecules are squished together more closely, held together more strongly under pressure, and so trying to melt is generally harder the higher the pressure is. Now there's one weird exception, substance you've probably heard of, water. There are a few other weird things, but that's the only one that we encounter significantly. Water and how it behaves is very, very important, kind of obviously for oceanography, but as we'll see, very, very important meteorology as well. And it turns out that water near its freezing point behaves a bit strangely on this regard. Ice is actually less dense than water. Oh yeah, you probably know that ice cubes float. But if we encountered more things as both liquid and solid, we would realize that that's quite unusual. Almost anything, if we had, say, a solid chunk of iron and melted iron, the solid iron would sink. Things like that. So water is actually quite unusual in this regard. This has some important effects. For one thing, that's how ice skating works. Ice skates, you do not want a razor sharp blade. You want something pretty narrow, but an actual flat bottom bit. And what that's doing is putting all your weight on just a little narrow bit. More pressure tends to melt the ice. So you're actually gliding along on a little bit of water. As you probably know, water on ice is quite slippery. And then as you skate on, then your pressure is no longer on the bit just behind you now, and it will freeze over again, and the next person can skate across it as well. Somewhat more important in the big scheme of things than being able to ice skate, because ice floats, that means that when things get cold, ice forms on the top of water and forms an insulating layer. Helps keep the water underneath warm enough to not freeze. Water not freezing is handy if you want to stay alive. So this is quite an important property of water to promote long-term survival of life on Earth. In contrast, if ice were denser, things get cold, the bottom of your lake or pond or ocean starts freezing, and gradually from the bottom up freezes solid. Not great for life. Again, pressure is always going up as you head down inside the Earth. Temperature generally increasing a little more regularly. And so because of this, we have the competing influences of pressure and temperature on what the layers inside the Earth are like. If we're looking at things physically and focusing on closer to the surface, which is most important for how the surface itself behaves, which is what we're trying to get back to, why the bottom of the ocean is like it is. The very top part is the lithosphere, lithos meaning rock. This includes both the crust and the top part of the mantle. And lithosphere, as you'd expect rocks to behave, is characteristically brittle and rigid. What this means is that when you put enough force on it, it breaks, which is generally what you expect rocks to do. Rocks usually aren't all that bendy, although depending on pressure and temperature and how slowly you do things, you can get some degree of bending in rocks. in the lithosphere, ultimately the end result is going to be breaking. The next zone under the lithosphere, we're getting hotter, somewhat higher pressure as well. This is the asthenosphere. It's still solid, about 1% is melted. So you would, if you could have a chunk of asthenosphere, it would be solid, not very fluid, but under those conditions it is, the technical term is plastic, but I tend to say squishy as perhaps conveying the idea a bit better. What this means is that ultimately, if you put enough force on it, rather than breaking, it will bend or flow in response to that stress. It's kind of similar to asphalt. I mean, you can walk on it. It seems pretty solid in that regard. But with enough pressure, it bends rather than breaking, especially if it's more hot. My mother-in-law encountered this relatively vividly. One time, it was quite a hot day. She was at the bus stop. She had fairly sensible flats on. A couple of other ladies waiting for the bus had spike heels. And as they stood there with all that pressure on the end of the spike sank down into the asphalt. By the time the bus got there, the spike heels were not leaving the bus stop. Underneath the asthenosphere, mesosphere, it's not as squishy as the asthenosphere, but there's still some capacity for flow due to the high temperature. And then again, underneath that, we eventually hit the outer core with its melted iron. Going on up to the top, we have the hydrosphere, the free water at the Earth's surface. Vast majority of this is the oceans. We do have, of course, some water in lakes and rivers as ice and glaciers, the water vapor in the air, groundwater in the spaces down in the ground. Free water, what do we mean? Well, there is water chemically associated with minerals in the crust and mantle. Sometimes if you heat those rocks, you can get water to come out. Sometimes it will take more drastic chemical changes there. So other water exists, or chemical that easily turns to water. There's some complication in how it's measured as well. But what we think of for water, actual liquid, that's in the hydrosphere. Atmosphere, of course, that's our gas surrounding the Earth, a mixture of various gases, mostly nitrogen, oxygen, with significant amounts of various others in there. Then the biosphere, this is the living and the relatively recently living dead material as well. Of course, things live in the water, in the air, down in the dirt. So biosphere overlaps with the atmosphere, hydrosphere, a little bit of the lithosphere. And of course, all of these are interacting with each other. The air, the water, living things, the rocks, these affect each other. So we need to keep these in mind as we look at any one, that we can't ignore the others. What are the differences that we need to be explaining here between the continents and the oceans? Elevation. Pretty obviously, the land's higher than the bottom of the ocean. But it's also not just continuous. The typical pattern of elevation in the two places is quite different. Something is going on differently about what's underneath. One of those differences is what those rocks underneath are made of. The types of minerals, the density of them, there are important differences that we'll look at there. And again, the types of features. We do not have mid-ocean ridges out on land. We don't see these trenches like the deep ocean trenches. What's going on to give us different types of structures down under the ocean versus what we see on land? That elevation difference. The average elevation on the Earth, there's something of a bimodal distribution. Bimodal means there are two peaks to it. That's one of the things that's wrong with Excel statistics. But at any rate, about 29% of the Earth's surface is land above sea level, 71% below. Out of that, the majority of land, as shown here, is at relatively low level, fairly close to sea level. And we also have appreciable shallow ocean areas. And then a lot of the rest of Earth's surface is roughly 5 kilometers down. We don't have a whole lot in these middle, roughly 2 kilometers down elevation, as well as not so much of the extreme highs and lows. Again, Mount Everest, below 9 kilometers up, Mariana Trench, about 11 kilometers down. So ocean is deeper than the land goes up. Okay, what are those areas made of? The continental type crust under the land in general, and also under parts of the continental shelf slope. These tend to be made of rocks such as granite and things chemically fairly similar to granite. Now, note where you're defining granite the way geologists do. If you are buying a countertop, then they tend to call anything that's not marble granite, some of which definitely is not granite in the geologic sense. So here we have granite is the actual one on the right, a related rock that happens to be more the volcanic version there, but same sort of composition. And so you see what the granite is like. Mostly light color. Yeah, there are some dark bits, but overall relatively light. The density is around 2.7 grams per cubic centimeter. For comparison, water is about 1 gram per cubic centimeter, depending on the temperature. Granite is an igneous rock, meaning that it's cooled from magma. It has a lot of aluminum. Like all rocks, we also have significant levels of silicon and oxygen. Basically, the vast majority of Earth rocks have lots of those in them as well. If we look at basalt, or gabbro on the right, pretty obviously there's a color difference. Darker. If you could hold them, what we do on the computer, you might notice that the basalt feels a little heavier for its size than the granite does. It's denser. Again, these are igneous. Basalt is typically formed due to volcanic eruption at near the surface, including under the ocean. the gabbro and the granite being ones that form somewhat deeper down under the Earth's surface. Still a lot of silicon oxygen, but not as much as the granite had. Only about 50% instead of 70%. And these have noticeably more iron and magnesium, which contribute to the dark color and higher density. By measuring earthquake waves, this was first noticed by a Croatian geologist, Mohovičić. Understandably, most of the rest of us call it Moho. This is the boundary between the crust and the mantle. And so, looking at earthquake waves, we notice an abrupt change. They get faster moving as we get past a particular point down into the earth. Underneath it, the rocks are even denser, around 3.3 grams per centimeter cubed. Still a lot of silicon and oxygen, but a little bit less still, and relatively high in iron and magnesium. So the mantle rocks are a more extreme version of the ocean floor type rocks. And in particular, its difference in density, this is an important player in why we see differences between up on the continent versus down in the ocean. And different density, well, given the opportunity, things that are less dense will tend to float up higher. Things that are denser will tend to sink lower. The asthenosphere, hopefully you remember, that's our squishy layer. So things can potentially float up or down on the squishy layer. It's not nearly as fast as floating on water adjusting, but it happens over time. Using water as a more familiar example, if we have blocks of wood of different sizes, maybe different types of wood, we'll see different patterns in how they float. And this adjusting up and down, balancing of something that is essentially floating is known as isostasy. You can imagine if you added weight, maybe pushed on one of these wood blocks in the water, it would sink. If you took weight off, float up. Now, if you've ever gotten in and out of a small boat, you've seen the effect here. So a taller block will tend to stick down and up more. A thinner block sticks up and down less. How much? Well, thickness, how dense our object is, denseness of what it's floating on. All of these play a role in the pattern that we see. No surprise, this depends on comparison between what's floating and what it's on. A very familiar example, we have ice, although it is less dense, it does float, but it's not that drastically different from water. And so only a little bit of the ice sticks up out of the water. This is quite familiar with regard to icebergs, the danger that a lot of the ice is underwater and unseen compared to what you see sticking out. If we make stuff around denser, well, that affects things as well. And that doesn't like it. Okay, so at any rate, I'm not getting a picture quickly there, but popularly account, Dead Sea, very salty, much saltier than the ocean. And if you try floating in there, quite a lot of you is sticking out of the water. If you pay very close attention, you might even notice that more of you sticks out if you're floating in the ocean versus in fresh water. So you're seeing that effect of the different material around determining how high or low things are floating. Because the asthenosphere is squishy, we have potential adjustment, isostasy, heavier stuff sinking down above, lighter stuff floating up more. The continent areas, again, continental crust is thicker, but less dense. So they tend to stick up more, which is why they're land, sticking out of the water. And also, they have deep roots sticking down underneath. Ocean rocks, much less thick for the crust. They are denser, and so they don't stick up nearly as much, nor do they need as much down underneath to balance what sticks up. So ocean crust, thin, denser. Continent crust, thick, less dense. If we change anything, then geologically it's typically relatively slow, but if we were to somehow add a significant amount of weight or remove it, then we do have long-term adjustment in the ground because of that. And some examples: glacier, huge miles thick mass of ice, that's heavy. And so the weight of glacier will tend to push down on the crust underneath it. If the glaciers melt, then things will rise up. We actually see the effects of this. Back in the Ice Age, we had glaciers getting down all the way as far as, say, northern Pennsylvania, southern England, weighing things down. So the areas that were under the ice, say Canada, Scandinavia, pushed down. Now that the glaciers have melted back quite a ways, those areas are rising up. And over time, if you, say, mark exactly where sea level is and then check back in a couple of centuries, well, you probably wouldn't, but somebody else could, and see that things are higher up. On the other hand, as the glacier is squishing down the most northern areas, that's tending to cause areas a little bit further to the south to be bobbing up in response. So areas like kind of mid-Atlantic states here, US, or southernmost England, central France range were the areas that were kind of pushed up by the glacier. Now the glacier's gone, those are tending to sink down, which means you have particular problems of erosion due to rising sea level because the land's sinking on top of that. Eroding mountains, that's less weight, things tend to move up. All the sediment eroded from the mountain piles up somewhere, adds weight, sinks things down. Big lakes, mountains. Another factor, cooling. Hot stuff, characteristic expands. Cooler contracts, is more dense. So rock that started out hot, as it cools down, it becomes more dense, it tends to sink. How do we measure these types of things? Briefly mentioned before, very precise satellite measurements of the sea surface pattern can actually tell us something about what the bottom of the ocean is like as well. Now, of course, you've got waves and tides, but if you make lots of measurements, average it out, you can cancel those. And it turns out that if you've got a mountain underneath the ocean, well, rock that's denser than just plain water. So you got a little stronger gravity there, a little more water. So there's a tiny bulge on the top of the ocean corresponding to a mountain underneath. Or if we've got an extra deep spot, say one of those deep sea trenches, water that's less dense than rock, a little lower gravity there, and ocean surface will be a tiny bit lower. You don't notice going up and down because of that on a ship. The waves are much bigger as far as affecting the ship, but again, precision satellite measurement can detect these and give us a picture of the sea floor. And that's the main source of the data behind a map such as that today. Some other clues: we can use seismic reflection, sound waves, essentially an echolocation, like what bats and dolphins can do. These sound waves can reflect off of the bottom of the ocean or even travel into it somewhat and bounce off of layers underneath. And sound waves travel at different speeds for different stuff, just like earthquake waves do. And so using this information, we can calculate how deep different layers are. So this picture here, yeah, these pictures tend to look like those magic eye 3D things when you haven't figured out how to make them 3D. They tend to be pretty messy looking, hard to figure out. But this one, well, you can certainly see there's sort of a bulge up here. It looks like there are layers curving up in the middle. So there's some sort of buried underwater hill down under the bottom of the ocean there. Okay, so what? Who cares if there's a buried underwater hill except some geologists? Well, it turns out that these features can be very, very important if you're trying to find oil. And oil, of course, you can sell for a lot of money. So there is quite a lot of use of these types of techniques. Basic idea: you need some sort of source of loud sounds, typically some sort of explosion, and you listen for echoes. You've got a sensitive microphone called a hydrophone in the water that is picking up on these sound waves, measuring the echoes, and then they can be analyzed to determine the layers there. Of course, explosions, loud noises, that can be a problem for things. Certain ocean creatures, notably various ocean mammals, that can be harmful for their hearing, cause problems with their own use of sounds. So do need to keep in mind possible impacts on marine life, not just be setting explosions off wherever we feel like it, but carefully consider the possible harm as well as benefits. Okay, so we've got our major parts of the deep ocean: continent margins, the deep oceans, mid-ocean ridges, each one of its distinctive features and parts. And these key features connect to the differences in types of rock underneath them. But why are those differences there? How do they form? And how can they change over time? That's our next big topic.